Hello everyone, welcome to YouTube channel MS Chem Insights by Dr. Aksa Habib. Today I am here to discuss second lecture of electrochemistry, that is about Nernst equation, its applications and its limitations. So let's start with the Nernst equation, which was introduced by Walter Hermann Nernst. This equation establishes a relationship between reaction quotient, which is actually the ratio of concentration of product and reactant, electrochemical cell potential, temperature, and standard cell potential. So the Nernst distribution law can be used to calculate the electrochemical cell's potential under known standard conditions of pressure, reactant concentration, and temperature because the cell potential fluctuates with these factors. Here is a general expression for Nernst equation where E naught is the cell potential at standard conditions, that is temperature 25 degrees centigrade, pressure 1 atmosphere, and concentration of reacting species is 1 molar. E cell is basically the cell potential at any given condition of pressure, temperature, and concentration. T is the temperature. R is general gas constant, and at standard conditions, its value is 8.314 joule per Kelvin per mole. N are the number of electrons which are involved in redox process. F is the Faraday constant and its value is 96500 coulomb per mole, and this is the concentration of oxidized species or product, and this is the concentration of reduced species or reactant. And this ratio is basically called reaction quotient. According to Nernst equation, the reaction quotient, which is basically the ratio of concentration of products and concentration of reactant, affects the overall cell potential of electrochemical cell. As the concentration of reactants decreases and concentration of product increases, the cell potential starts to decrease due to utilization of batteries EMF. Nernst equation at standard condition, that is 25 degrees centigrade, can be written as this by putting the value of R, that is 8.314, temperature 298, and Faraday constant 96500, and converting this natural logarithm into log base 10, we get this equation, and we can write the concentration of product and reactants ratio as Q. So according to Nernst equation, the reaction quotient determines the overall cell potential of electrochemical cell. Let's discuss how Nernst equation can be helpful to determine equilibrium constant. In the electrochemical cell, when equilibrium reaches, the value of change in Gibbs free energy, that is delta G, becomes equal to 0. So at equilibrium, reaction quotient can be written as Kc, that is equilibrium constant, and as we know, delta G is equal to minus NFE, that is electromotive force of cell, and at equilibrium delta G is equal to 0, so EMF will also be 0. So putting the value of reaction quotient, that is Q is equal to Kc, and EMF is equal to 0, we can write the Nernst equation as this. So from this equation, we can write the EMF of the cell at standard conditions like this, and from this equation we can separate log Kc, which becomes equal to N E naught over 0.0592 volt. So the relationship between standard cell potential and equilibrium constant is obtained. From this relation, we can deduce that when the value of Kc is larger than 1, the value of standard cell potential will be greater than 0 because the log Kc will be positive. It means that the reaction will be favored in the forward direction. While If the value of Kc is less than 1, then log Kc will be in negative. So the standard cell potential will be in negative, which means that the reaction is not favored in forward direction, but it is favored in the reverse direction. So with the help of this equation, we can determine the possibility of forward or reverse reactions. Nernst equation is very important in electrochemistry due to its various applications. For example, this equation can be used to calculate the single electrode potential at any given condition. For example, this is a reduction process in which metal ion is getting reduced by gaining the electrons. For this reduction half process, we can write the Nernst equation like this. From this equation, we can easily calculate the reduction potential at given conditions. This is the standard potential which we can obtain from the electrochemical series, and by putting the values of these constants and concentration of product, that is this one, and reactant, that is this one, we can easily determine the reduction potential at given conditions. On the other hand, if we know the reduction potential at given conditions, we can determine the standard cell potential with the help of this equation. Nernst equation is also useful to determine the overall cell potential, which is actually the difference of cathodic cell potential and anodic cell potential. With the help of Nernst equation, we can also determine the feasibility of a redox process. As I have already discussed in my previous lecture, with the help of an electrolytic cell which contains zinc as an anode and copper as a cathode. So putting the value of cathodic potential, that is 0.7618, and anodic potential, that is 0.3419, we can calculate the overall cell potential, that is positive 0.4199 volt. So the positive value of cell potential indicates the feasibility of that electrochemical cell. With the help of Nernst equation, we can also calculate the concentrations of ions if we know all other values or factors. With the help of Nernst equation, we can also determine the solubility product of a sparingly soluble salt. For example, we have a salt AB which dissociates as A positive and B negative. For this equation, solubility product can be written as the product of concentration of A and B. As we know, the Nernst equation is written as this, in which this Q is reaction quotient. We have to separate this reaction quotient. So this relation becomes like this. And in order to get rid of this natural logarithm, we have to write this whole part as a power of E. As we know that at equilibrium, the reaction quotient becomes equal to equilibrium constant, which in this case is solubility product constant. So from this equation, we can calculate the solubility product of a sparingly soluble salt. Nernst equation is also helpful to determine the pH of a solution which involves hydrogen ions. So the reaction quotient can be expressed in terms of concentration of reactants and products including hydrogen ion concentration. For example, this is a reduction process in which chromate ions and hydrogen ions are getting reduced and this product is formed. The Nernst equation for this process can be written as this, where the hydrogen ion concentration is written in denominator, and as we know that the negative log of hydrogen ion concentration is equal to pH. So from this equation we can easily determine the pH of that particular solution. Although Nernst equation has various applications in electrochemistry, but it is not free of shortcomings. For example, the Nernst equation is proposed for dilute solutions, which are also called ideal solution in the case when the ions exist as individual ions where there are no force of attraction or interaction exists between the ions. So for dilute solution, the ion concentration may be taken as the activity of ions. But for the concentrated solution, the ion concentration is not equal to its activity due to electrostatic interactions between the ions, which may cause ion pairing and may increase the viscosity of the solution. Thus, the solution of electrolytic cell may deviate from its ideal behavior due to change in activities of the ions in the solution. So the Nernst equation, which is used to calculate the cell potential, here the cell potential may change due to change in concentration of ions in the case of electrostatic interactions. So in order to calculate the cell potential of concentrated concentrated solution of the cell, we have to take the help of experimental measurements in order to calculate the true activity of ion for the electrolytic cell which contains concentrated solutions. The second shortcoming of Nernst equation is that it cannot be applied to the cell for calculation of electrode potential where current is already flowing through the electrode, because the current flow affects the ions activity on the surface of electrode, which changes the reaction quotient, and thus overall cell potential may change if the current is already flowing through the electrode. So in such case, we have to first determine the current flowing through the circuit with the help of ammeter, and using the Ohm's law, that is equal to V is equal to IR, we have to calculate the potential and then we have to subtract that potential from this electrochemical cell potential. This was all about Nernst equation, its applications and its limitations. If you have any question or query, please drop your comment in the comment box or write me an email at the email ID given in the start of this lecture. Thank you very much for your attention.